I left this in your notes because it is instructive on how to do this after you've worked an example. That's the formula for how to do what we're going to do. Basically what this says is we're going to calculate an integral from point A to point B by taking the antiderivative of f of x, in other words the integral, and then once we get the antiderivative, which is capital F, we're going to evaluate that integral at B and at A and subtract the value at A from the value at B. And the notation that they usually use is the antiderivative of x from A to B. And that's kind of carries in with the way some of the TI-84s show it. The fundamental theorem doesn't require that the function be positive. It's only necessary to find the area to assume that it's positive, but it doesn't define the definite integral. It just gives a method for evaluating it. So we're going to go ahead and do one so you can see how this works. It says find first the integral of 4t to the third dt. Now, rather than go through the PowerPoint part of it, I'm going to switch over and do this problem on the overhead for you, so it'll slow me down and give you a chance to write. So this is what we're going to do, and we actually are going to need the calculator, so I'm going to leave it hanging out up here to the side for us. So we're going to do the integral of 4t to the third. This is just a power rule problem. So you take 4t, add 1 to the power, 3 plus 1, divide by the new power, 3 plus 1. Good. Oh. That's weird. And then that's actually 4t to the fourth. Why are you doing that? Let me try something. Maybe I'll have to restart it. Oh, there it is. I may have to restart it to get it to behave itself, though, because it's not picking up. Let me pause the recording. Okay. So, 4t to the 3 plus 1 is 4t to the fourth power over 3 plus 1 is 4. And guess what happens to the fourth? And then normally, if we're doing the indefinite integral, then we would say plus c. So this integral is equal to t to the fourth plus c. Now we're going to move over and add the part to it where we're going to do the definite integral. This is capital F of x. That's your antiderivative. What we're going to do is we're going to take capital F, not capital F of x, it's f of t, I'm sorry. Unlike y'all, I think they ought to use x and y all the time. It's just simple. F of the higher one is what you start with, so f of 1. Is that actually the way they did that?
No,
did I have it back? Okay, I have it backwards. Okay, then let's change that. I copied it down wrong. Should be 2 on top and 1 on the bottom. So we're going to take capital F of 2 minus capital F of 1. And here's the reason you don't have to add plus C. F of 2 plus C minus F of 1 plus C says that you're going to have F of 2 plus C minus F of 1 minus C, and guess what happens to your constants anyway? They drop out. So all we're really going to evaluate is this. So F of 2, that's 2 raised to the 4th power minus 1 raised to the 4th power. 2 to the 4th power is, I believe, 64. No, it's only 16. I was way off. So it's going to turn out to be 15. Okay? There's your whole solution. Anything anybody doesn't understand? Yeah, the calculator is even easier because if you do, go to your math menu, go find your function integral, plug in your function, you just have to use x, 4x to the 3rd, it actually has a 3rd power on this thing, with respect to x, from x equals 1 to x equals 2, close the parentheses and hit enter, and it says, oh, guess what, it's 15. Sure, just be sure and show me what to put in, because if you happen to switch the last 2 numbers, it'll give you a negative answer, which should clue you that you did something wrong, but might not. So yes, you can use it on, I would encourage you to use it on the test. Okay? So that's everything that we did right there. That's just the notation for it. And this is an explanation of why you didn't need the C. And I'm going to skip over that part because you don't really need to worry about that. This is the derivation. This is the properties of definite integrals. And what you'll see here is this is the exact same list that I gave you at the end of section 15.1. The only thing is now there's endpoints. Okay? But it's the same ones we've had before. So what we want to do is, let's see. Basically, this is some English on some of it. For all functions equal to or greater than 0, the distance from A to A is going to be 0. So the 3rd property says the area under a graph bounded by X sitting in one point is 0. Well, duh. That's not area, that's a line. Lines don't have area. And since this represents the blue region in figure 17, from A to C, if you wanted the total area here, you could do the integral from A to C plus the integral from C to B and break it up. And that is going to be important later. So we'll look at another example. We have the integral from 2 to 5 of 6x squared minus 3x plus 5 dx. So we're going to break this up to do the integration, but I'm going to do the indefinite integral before I actually worry about the constants there. So we're going to do the integral of 6x squared minus the integral of 3x plus the integral of 5, and all of those have dx on them, indicating that those are derivatives. So in other words, we're going to integrate just like we do derivatives, one term at a time. So the integral of 6x squared is 6x to the 2 plus 1 over 2 plus 1 minus the integral of 3x is 3x to the 1 plus 1 over 1 plus 1 plus 5. And remembering that this started out being no x's there, we're going to add 1 to a power of 0 and then divide by 0 plus 1. So the value of that integral is 6x cubed over 3, not 2, 3, minus 3x squared over 2 plus 5x over 1, or more cleanly, 2x cubed minus 3x squared over 2 plus 5x. And at this point, the efficient way to put the definite integral in is to say that we're integrating this from 2 to 5. So that means we're going to take 2 times 5 to the third power minus 3 times 5 squared divided by 2 plus 5 times 5. And we're going to subtract from that 2 times 2 to the third power minus 3 times 2 squared divided by 2 plus 5 times 2. And 2 times 5 cubed is going to be 250. 3 times 5 squared is going to be 75 over 2 plus 25 minus 2 times 2 cubed is 2 times 8, which is 16, minus 3 times 4 is 12 over 2 is 6, plus 5 times 2 is 10. And I'm now going to abandon all my arithmetic in my head and use calculator. Now I'm going to see if I'm right. So let's see the original function. Yeah, I see it now. This mouse has gotten to where it wants to either double things or skip things. Comma x, comma 2, comma 5. And I must have done something right. Okay? So the steps are all listed there, and we'll try another example. This one's actually got the answer on there, so maybe I'll just go ahead and explain how we're doing this one, because this is one we're actually ignoring the 2 and the 1 for the moment. You've got the derivative of y over y. In other words, that is the integral of 1 over y dy. Okay? And the integral of 1 over y is the antiderivative of 1 over y, which is the natural logarithm of y. Remember, 1 over x and ln x are the derivative twins, okay? So that means what I'm really going to do here, and it says the absolute value. In truth, you don't have to really worry about the absolute value unless maybe your endpoints are negative. And then you do have to worry about the absolute value. But I'm going to evaluate this at 2 and at 1, and the natural logarithm of 2 minus the natural logarithm of 1, you can verify this on your calculator, is equal to 0.6931 minus 0, because the natural log of 1 is 0. Now this is one where we're going to have to do some substitution, so it's probably good to do a little practice of that. We're going from 0 to 5, and we have the square root of 25 minus x squared, and then we have x dx. And I personally always think they're being sneaky when they write that x there in the front, because I always rewrite it as soon as I start by putting the x over there away from that square root. So if this is u, then du is negative 2x. I don't have the negative 2. So in order to have it, what I'm going to do is I'm going to put negative 2 right here, and then I'm going to put negative 1/2 on the outside. Because if what I put in is negative, I take the reciprocal, but it still has to be negative. And then that's going to be 25 minus x squared negative 2x dx. And this negative 25x squared is raised to the 1/2 power. So now that is turned into the integral of u to the 1/2 power du. But remember, these values here are x values, they are not u values, so you've got to go back and put your substitute back in when you're done. So the integral then is going to be u to the 1/2 plus 1 over 1/2 plus 1, which is equal to u to the 3/2 divided by 3/2, which is multiplying by 2/3, so it turns out to be 2u to the 3/2 divided by 3. And now I need to go back and put my actual value of u back in. So that's going to be 2. Oh, that's supposed to be 2. That's going to be 2 times 25 minus x squared. To the 3/2 power, and that's all divided by 3. And then we're going to evaluate that at 0 for x and at 5 for x. So we'll have 2 times 25 minus 5 squared to the 3/2 power over 3 minus 2 times 25 minus 0 squared to the 3/2 power over 3. There's your next step, which means then all of this is just 0.
Did we already figure the negative 1/2 over?
No, we did not. No, we did not. We did not. Let me put the negative 1/2 in. Because that should have actually been, yeah, 1/2 times that, and 1/2 times that, and 1/2 times that,
It's a negative 1/2.
and it's a negative 1/2. Which means that our integral was actually negative 2u to the 3/2 over 6. So that's going to change all of those. But even after going back and correcting all of that, this turns out that when you evaluate this at 5, that turns into 0. And 0 to a power is still 0, and when you multiply it by negative 2, it's still 0. And when you divide it by 6, it's still 0. This is going to be minus a negative, so this is actually going to be positive, and I'm glad you caught that because I was sitting here thinking, I know I've done something wrong, this area can't be negative. So, in order to do this in my head, rather than on the calculator, and then I'm going to check it on the calculator, 3/2 power means I'm going to take the square root of 25 raised to the 3rd power. And that is equal to 25 times the square root of 25. And then I'm going to multiply it by 2. And then divide the whole thing by 6. And since 2 goes into 6 3 times, I'm going to leave that as that. And now, let's see, I've got 25 times the square root of 25 is 25 times 5 divided by 3, which is 125 divided by 3, and that's not going to come out even. Oh yeah, you can do that one on the calculator.
Will you show us how?
So it turns out to be about 41 2/3. So if we do it on the calculator, we go back up here to the top. I want a lot of A's on this next test. Yeah, I do.
If you wouldn't put all that other crap, I might have it.
That's really hard to give us an
A for effort, right? When you get to do that little line, that was almost equal. That didn't sound nice.
I wasn't trying to be not nice.
Well, at least you're honest.
I will give you what you earn. I will never give you less than what you earn. Sometimes I'll give you a little more than what you earn because you worked so hard.
Is the 84 the same? I mean, you gotta put.
Yeah, the 84 just looks different, but you go back to that screen that I showed you what it looks like. It has little boxes for you to fill in.
But I couldn't figure out how to get the X in front of the square root and extend
I'll show you.
it. Okay.
Do you not have to do? the
Now
square
that,
root? Do you
yeah, I'm trying to look, it's,
Do you
what,
not have to do the square root of it?
A. It's the square root, but
You just got 25 minus the X
it's the
squared.
square root of 25.
well, and I put in to the 1/2 power, but somehow I don't think it liked that. So let me regroup and actually do it with a square root function. That's simpler anyway.
Oh, you're missing an X in front of the square root, because you moved it originally.
Oh, yes, that's right. That's the bad thing about moving is when you put it back in the calculator, you forgot you moved it. Okay, and that is the right answer. Just remember to put in the actual original function.
Will you show us on the other calculator?
Um, on the power, well, yours doesn't do it, does it? Does yours?
Mine doesn't.
Okay.
Anybody weird?
No, mine at home, my TI-84 that I have at home does like yours does. It doesn't do this one. I think it's the pluses and the C's that do it the right, what I would call the right way. You still get to it the same way. I'm going to quit and then go math. Choose number 9. That's the same on the 83, the 80, and any 84. But then if you've got the newer one, it brings it up this way. So you enter the 0. Oops. Let me clear that and try it again. So you start out entering the 0.
Wait, how did you get all that stuff already up there?
I hit second enter on hers. Let me go from the beginning again. So you start out entering the 0. And then put in the 5. And then put in your function. Don't forget the X. And then you put the x at the end. So it just looks different. And there's the answer.
Okay, thank you.
So we don't have much time left. Let's see. And what we just did was the second method. We didn't do the first method. And it winds up being, as we said, 125 over 3, which is 41 2/3. And it says, don't confuse the two methods, because what you're doing in the second method is you're actually going ahead and putting in what U would be. And I left it in the PowerPoint because some people like to do it that way, but I don't do it that way. I do the U substitution and then do the numerical conversion at the end. They figure out what the actual value of U is going to be for X is 5 and X is 0. I just think that's backwards. And it is a powerful tool. There is a limitation. Not every function has an antiderivative in terms of functions and the operations that you've seen so far. And for example, you cannot evaluate this particular integral with the fundamental theorem, but it's used in the probability and statistics formulas. It just takes another way, but the ones that we're going to have, you're not going to have to worry about those. The only thing I want to be sure and point out to you, and then I can finish this up and put it in, I'll be doing it with my other class, so I'll put it in integrity from the other class, plus I'll finish it up and put it in Shobi for you too. I'll pick up from here. There is one caution. This function, x squared minus 4, if you evaluate it from 0 to 2 or from wherever to wherever, the problem with this function, or not this function, that's the wrong graph, sorry. There's nothing wrong with that one, that one works just fine.
So this is not in our notes, right?
It should be. Do you not have these notes?
Yeah.
So page 13.
Yeah.
Page 13?
Example.
Okay, just, this one wasn't supposed to have the graph where I put it in the PowerPoint. I accidentally put the PowerPoint graph in the wrong place. Okay, here's a graph where, remember, it's the area of the region between the x-axis and the graph of x squared minus 3x when you go from 1 to 3. Well, the problem is when you graph f of x going from, and then look at the area from 1 to 3, that area is under the x-axis. It is not above it. So when you actually do this problem, what you wind up doing is you're going to have a negative answer. I mean, the integral's not hard to get because it turns out to be x to the third over 3 minus 3x squared over 2. And when you plug in 3, that becomes 27 over 3 and 27 over 2. And then when you plug in 1, it becomes 1 over 3 and 3 over 2. And that answer comes out to be negative 10/3. The actual area, though, the actual blue area, is the absolute value of that. And that's what that other example was mentioning, is that you sometimes you'll have to take the absolute value of what you get at the end, because it will interpret area under the x-axis as being a negative area. Okay? So remember, area is always positive, it's never negative. And then the one remaining thing to be cautious of is, in this case, we're talking about x squared minus 4 from x equals 0 to x equals 4. And here we've got a real problem, because part of the area is under the x-axis and part of it is above the x-axis. So the way that we're going to have to do that problem is knowing that that's going to give us a negative area. So one of the ways that you can do this is you solve the equation x squared minus 4, which is your function value, for 0 and then actually break that integral up, instead of going all the way as it originally says from 0 to 4. Realize that it's going to have a value of 0 at x equals 2. So that's where it's going to cross the x-axis. What you want to do is you want to break that area up and go from 0 to 2 where it crosses the x-axis, and then from 2 on to 4 where it rises above the x-axis, and take the absolute value of those areas, make sure they're both positive. So when you actually finish out these calculations here, it comes out to be positive 16, which is what it should come out to be. Okay? And you don't have to worry about this area coming out negative, it won't, but this one will. And if you don't look at a graph, that's why I mentioned earlier once, graph the function in the integral, graph it first, and look to see if it dips below the x-axis. And if it does, find out what that x-intercept is. You can use your calculator to find it. You don't have to solve something set to 0. You can just use, tell it to find your 0 for your function, go to the left and right of it, and it will give you that value. But then break your integral up into that first interval and the second interval. So if I were doing this problem without worrying so much about the calculus, if I were going to do the preliminary work here, this is the important thing. I would go to y equals and graph y equals x squared minus 4. And I would want to set my window, since my interval is from 0 to 4, I'd want to make sure that I could see all of that. So then I would go like maybe at least -1 to 5. And I would just hit graph initially to see. So what I'm seeing here is there's a little bit of area below the x-axis, and then there's going to be a whole bunch of area above the x-axis. So what I probably want to do is make it taller for one thing, so that I can see all of it. So at x equals 4, just so I can see where it is, that's right there. So the area is from here back to here, and this little area here, and this is going to be negative. So I have to be careful when I do the integral to take the absolute value of the first piece of it. And if I want to find that x-intercept, you go second, trace. The name of the intercept is called its 0 point. Move your cursor to the left of the 0 point. You have to get below the x-axis, or to the left of the point really is the better way to say it. So I'm below the x-axis. I'm to the left of the point. Hit enter. Move it to the right of the point. Hit enter, and as long as those two things point at each other, you're good to go. Press enter and it'll find it. And it says it's 0 is x equals 2. So you want to break this interval up from 0 to 2 and from 2 to 4. Okay? And make sure you take the absolute value. And the reason you need to be sure and do that is because if you simply do that integral numerically without looking at that graph, and just plug this in, it's gonna give you the answer 16/3, which is not right. It's actually much larger than that. Okay?
What's the answer supposed to be?
Um, 10 over, no, that's not it. Where's the right answer? 16. Just be sure you take the absolute value of the first piece of the integral. And I will put a recording and show you, and I'll actually go back over this one again and show you that on the calculator, you can make it do it numerically the correct way. What you want to do is to remember that if you've looked at the graph and see that you've got some below and some above, that you take that first integral and take its absolute value. And then you do the second part of the integral and just add them together. So I will see all of you next week, and I will try to get caught up on all of everybody's questions.
And you can go in and look at the homework to adjust it.
Yeah, let me look at that as soon as I get home tonight.
Because I'll start 53 tomorrow.
Okay, I'll look at it as soon as I get home tonight.
How many